today we'll show that the alternating harmonic series will converge, and exactly that it will converge to ln 2. Well, the alternating series, if you don't see the pattern, it's always taking the reciprocal of the natural numbers, but then alternating one. So in summation, let's just call this S. In summation notation, we can say k is equal to 1 up to n. So we get negative 1 raised to the, well, that's k plus 1, and then all over k, because we start with a 1. And this is actually Sn, because we want this to go to infinity, right? So we can actually already just rewrite this. First of all, we want just the even terms. So this is k is equal to 1, but then we just use the 1 over 2k part. And then we subtract another sum from k equals 1 up to n, 2k plus 1, 2k minus 1 actually. Exactly, so that's just, you have just the 1 here, we start with, well, so actually that's negative and this is positive because we have the odd term and then the negative and then plus and everything works out. So in order to solve this, we need to look at another series which is called the harmonic series. And the harmonic series is just equal to 1 plus 1/2 plus 1/3 and so on. This actually diverges. By the way, we already know that this converges because the terms of the absolute value are getting smaller and they are alternating, so this has to converge because of the Leibniz criteria. And the harmonic series helps us here because we can realize that this, well, that's just equal to 1/2 times, we take the 1/2 out, and then we get the harmonic series, which is just h sub n of n. Yeah. And for this we can do something similar. Well, let's just write out a few terms. This part here is just equal to that, but now we can add a 1/2 here and a 1/4 here, and just add the harmonic, just 1/2 times the harmonic numbers. And well, in general this will go to, because we have n times and here also n times, this will just be equal, well, if we add both of these, this will just be equal to h of 2n, because we are going to 2n. But we can get this to the other side, so we say this is minus 1/2 times h of n. And now all of this, we get Sn is equal to 1/2 and 1/2, that's just negative 1, negative hn plus h2n, right? So now let's take something I'll prove later, but what we need is that h of n minus ln of n actually converges as n goes to infinity. And it doesn't matter what this converges to, but we call this gamma, anyway. So we will introduce the ln here. Okay, so this will be equal to h2n, and then we just get out of nowhere a ln 2n, which we will subtract in a second. But then we need the minus hn, and then plus ln n, right? And then we need to add back the ln of 2n and subtract the ln of n. And if you trust me that I was right, then this, as n goes to infinity, well, that's just equal to gamma, because 2n doesn't change a thing about, right? And here, still, if you trust me, n goes to infinity, then this will go to negative gamma. So these two will just cancel away, and we are left with is this. Well, then we can take it all to 1 logarithm, and then we just can cancel the n's, and this is ln of 2. And that's what we needed to show. Now we just need to show that gamma converges, that the harmonic sum minus ln converges. a fixed value. Okay, so now we just need to show that the gamma value converges. So in order to show this, we will define a gamma n, which is just the harmonic number minus the logarithm of n. Now we want to show that first of all this is monotonically decreasing, and then it's bounded by, well, some value. Okay, so to show that it's monotonically decreasing, we need to show that gamma of n plus 1 minus gamma of n should be less than 0. So we will just plug in the definition here. So this is h of n plus 1 minus ln of n plus 1 minus h n plus n plus ln n, because minus minus plus. Now we can get these all together. This is the harmonic, so this is 1 over n plus 1. And this just becomes, where we get ln n minus this, so this is ln n over this. That's just logarithm rules, and because we use this, that's a plus. So now we want to show that this is less than 0. First of all, let's get the ln to the other side, n plus 1. And because it's a minus ln, we will just invert whatever's inside the parentheses. Now we e to the power of both sides, so this cancels. So we get e to the power of 1 over n plus 1 is less than n plus 1 over n. And now we will use a nice tool, which is the series approximation of e to the x, because e to the x is less than 1 plus x squared over 2. Because normally there would be no more terms here, and we just cut them off and they are positive, so this equation holds true. So we will plug this in right here. So we get this, that this is lesser than 1 plus 1 over n plus 1 plus 1 over 2n plus 1 squared. Okay, and the right hand side stays the same. If we show this, then this holds true. So we get negative 1 to both sides, and we just write this as n over n. So this also cancels, which is nice. And now we will multiply this by 2n plus 1. So this is 2n plus 1 over the denominator is now the same. So we can get 2n plus 1 squared. And this just stays 1. And over here we have 1 over n. Okay, so we will multiply the reciprocal. So this is 2n plus 1 plus 1 all times n, and this should still be less than 2n n plus 1 squared. Now we just multiply all of these out, so this is 2n squared plus 2n plus n should be less than, what's this, n squared plus 4ab n plus 2. And so we get that this cancels out and one of them cancels out, so we have 3n, so we have 3n is less than 4n plus 2, so we can just cancel this out, and this equation, this holds true. So now we need to show that this is bounded by 0. We will now use the mean value theorem. So for ln, in an interval of 1 and x, there will exist some value c, where we know that ln prime of t will be equal to the average slope, which is ln of x minus ln of 1. all over x minus 1. So this is just 1 over c, right? And ln x, this just is 0. So we get that ln x over x minus 1. And exactly, this value is always, because c is in 1 and 0, so we get that this is lesser than 1. And then we multiply by the other side, so x minus 1 equals smaller than ln of x. And exactly, that's what we use. So exactly, we'll use that ln when we can just plus both sides, so we get x plus 1, do a substitution here, is bigger than x. And now we will use a x equals 1 over k, so we get ln of 1 over k plus 1 is bigger than 1 over k. And now we can do something fun. We can pull out a 1 over k here, and this will give us 1 plus k. It's bigger than 1 plus 1 over k. And because that's multiplication, we can do ln of 1 over k plus ln of 1 plus k is bigger than 1 over k. And because that's negative, we can just get that ln of 1 plus k minus ln of k is bigger than 1 over k. Sorry, I made a mistake. Before I made the 1 over c greater, so the equation was on the other side, so all of these become a smaller than. Exactly, and now we can sum up all of these terms. So we get k equals 1 up to some value ln of 1 plus k minus ln of k is smaller than the sum of k equals 1 up to n over 1 over k. But hey, that's just the harmonic numbers of n, right? And here we get something nice. That's an telescoping series, because we have, well, we can write it out a few terms. So we plug in 1, 2 minus ln 1 plus ln 3 minus ln 2 and so on. So we just get, so this will cancel out this, everything will cancel out except the first term, which is minus ln. So we get that this holds true, and now this becomes 0. Exactly, so we get h of n is bigger than ln of 1 plus n. So now we will introduce the other minus ln n, and well, that's bigger than ln of 1 plus n minus ln n. And this will just be gamma of n is bigger than, what's this, ln of 1 plus n over n. And exactly, this is always positive, so we've concluded the proof.